Good afternoon, this is Joan Park, and I am a first-year master's student. Today, I will be introducing a paper titled Online Diffusion-Based 3D Occupancy Prediction at the Frontier with Probabilistic Map Reconciliation. The definition of reconciliation might be unfamiliar, and it refers to the process of making different sources of information consistent with one another. I chose this paper because I am interested in applying probabilistic generative models to robotic problems. At ICRA, we have seen generative models used in various areas including trajectory generation, like planning in latent space, or scene and map generation using like conditional diffusion, and skill learning, where policies are learned or guided through sampling. These works show the growing interest in using generative models not just for motion, but for world understanding and high-level reasoning, which is closely related to the paper I will present today. Among them, last year's Simpson's paper proposed a method that uses a diffusion models to predict occluded or out-of-sight cells in a 3D occupancy grid map. The author, Alec Reed from a University of Colorado Boulder, suggested that the Simpson's model could be used to aid planning tasks. And this year, he released a follow-up paper that applies that idea directly in practice, which is the work I am presenting today. This paper proposes a real-time navigation framework for predicting 3D occupancy grids beyond the sensor's field of view using a modified diffusion model, and merging the predictions with observed maps using a probabilistic reconciliation rules. In autonomous navigation, robots are limited by occluded spaces. As a result, robots often engage a redundant exploration to verify unseen spaces, slowing down the overall navigation and making the exploration inefficient. To solve this, the authors proposed a method that predicts occupancy grids beyond current observations and merges the predictions with the existing occupancy map using a probabilistic update rule that preserves consistency and allows multiple predictions. The overall system pipeline is structured as follows. The robot first builds an occupancy map from sensor data. It then constructs a graph to identify frontier points. At selected frontiers, a diffusion model is used to predict occupancy. And finally, the predictions are merged into the map using a probabilistic update rule. Now let's focus on what happens after the robot uses Simpsons to predict occupancy in unexplored regions. Since Simpsons is based on a diffusion model, its predictions are inherently stochastic. Even with the same input, it can generate different plausible outcomes. And how do we handle the uncertainty and variability of generative predictions when updating the map? That is where the probabilistic map merging method comes in. To handle this variability, the system applies a Bayesian-style update rule that probabilistically merges each new prediction with the existing map. This rule updates only on observed voxels, ensuring that sensor data is never overwritten. As multiple predictions are fused over time, the occupancy estimates become more refined and consistent, resulting in a more reliable map. And the next question is, where should the robot predict? To answer this, the system builds a graph over the current map and evaluates each frontier node using the exploration gain formula. The idea is to prioritize frontiers that offer the most information while minimizing the travel cost. Each node's score depends on how many unknown voxels it can see, and it is penalized by how far it is from the robot and how misaligned it is with the current exploration direction. The authors conducted experiments in two indoor environments using a real robot. They tested different ways of selecting where to predict and different strategies for merging predictions into the maps. The results shows that using probabilistic merging improved prediction accuracy, and even predictions made in unexplored, distant areas were quite reliable. However, the system was only evaluated within their own framework, and while they claim this approach helps exploration, there is no actual metric showing improved exploration performance. And this is end of my presentation, and thank you for listening.